Hello and welcome everyone to the presentation on how to do cost modeling using the tool developed by GIZ. Today we are going to talk about how the tool has been developed, what has gone into it, what are the different configurations that can be done to be able to calculate the cost of ammonia. Before that, I will just start with a brief introduction about myself. I am Siddharth Jain. I am Managing Director and founder of MEC Plus. MEC is a consulting company working in the renewable sector for the last 10-15 years. We are working with private as well as public companies and helping them invest into the renewable and hydrogen sector. Today, the agenda is to cover 4 elements in order to give you a demo on the modeling of green ammonia costs. First, we would want to talk about what are the inputs and outputs that are there in the model and how you can configure them to create outputs. Then I would want to take you through the dashboard to tell you how the Excel looks like, what are the inputs and outputs and how are they configured in the Excel. Then we will run 3 cases so that we can see how the model can be configured and what sort of outputs does it give us. And then I will take you through the background of all the sheets that are there so that you can see how the inputs are gathered, how you can change them, and how do they then come into the final cost calculation. So to start with, this is how the dashboard's outputs look like. The dashboard's outputs are configured for ammonia, hydrogen, and renewable power. It gives 3 kinds of outputs. First is the annual production that is possible from the plant, be it the ammonia plant, be it the hydrogen plant, be it the renewable plant. It then calculates the cost of production of ammonia, hydrogen, and renewable power and compares it with the cost of ammonia with blue ammonia as well as gray ammonia. For the cost of production of hydrogen, it calculates the cost for production against gray ammonia and blue ammonia, and then it calculates the cost of renewable power, that is how much is renewable power cost totally produced and how much renewable power is consumed as the cost there. So if there are any wastages of renewable power that is there, they are taken out and the cost is given as to the consumed cost power from the renewable power. And the third output that it gives us is the operational profile, that is how the plant is running hour on hour during the entire duration of the year. What is the source that is supplying? Is it the battery? Is it the grid, or is it the renewable power plant? And then also what is the way the renewable and hydrogen production plants are working hour by hour. It also calculates the cost for production of urea, DAP, and NPK, the 3 fertilizers, and calculates the breakup of the capex of the ammonia plant into constituting elements and the contribution of each of the capex and the opex elements into the final cost of hydrogen and ammonia as waterfall charts. In order to calculate ammonia, there are at least 25 parameters that are required to be simulated and modeled. This model takes into account 14 parameters. The way the model has been structured is that it calculates the cost of electricity based on a renewable plant that has been configured and the different technologies and the size considerations that are there. On the basis of that, it calculates the cost of hydrogen. Then the cost of hydrogen is then given as an input to the cost of ammonia. And finally, we get the cost of levelized cost of ammonia based on green hydrogen, which is based on green electricity. There are many configurations that are possible. This model simulates the cost of ammonia around 14 parameters. These being the definition of green ammonia, whether green ammonia is derived from hydrogen, which is monthly settled or hourly settled. The year of commissioning of the plant, we have taken a timeline of 10 years. The technology for RE that has been used, whether it is standalone or a combination of 2 technologies along with battery. The plant configuration, whether the plant is directly connected to the RE plant or is it connected via the grid. The reason why this has been included is that when we add grid, we get better flexibility and better power prices, but we also have to pay grid losses and grid charges. These have been calculated for all the states in India, and hence RE plant location option has been given to be selected for all the states in India where there is good resource. The balancing technology that has been used when RE is not there, whether we are using banking or not banking, what kind of electrolysers are being used in the plant, alkaline or PEM, whether there is an oversizing that has to be done for the electrolysers, depending upon the RE configuration, or we use that electricity for some other reasons that is given as a user input. The curtailment rate that the RE plant is likely to see on the grid, the financial parameters, that is debt to equity ratio, the rate of debt, the target IRR, the resulting work back that will come up. What is the source of CO2 that is to be used? Is it something that is indigenous to the urea plant coming from the gas turbines, or whether it is to be sourced from outside? This is for DAP, NPK and fertilizer urea cost, primarily for urea. DAP, NPK do not use it. Then the RE plant and battery configuration, whether we want to oversize the RE, whether we want to change the solar and wind ratio, or whether we want to add any battery capacity for our own business requirements that might be there. What are the additional revenue options, whether they have to be considered as part of the cash flow statements, and the water source that have been used in order to run the ammonia plant. I will take you through the dashboard. This is how the Excel model looks like. It has a cover sheet which gives some basic introduction to the model. It has a guide sheet which talks about the structure of the model and how the model is configured, what are the different sheets, purpose, and how you should sort of treat the cells. And there are two dashboards, one for D1, which is ammonia, and another D2, which is renewable energy. The difference between the two dashboards is that the ammonia dashboard takes the user as the someone who is interested in setting up a certain amount of ammonia plant and has a certain location in mind to set it up and wants to calculate the cost of ammonia. The D2RE dashboard is for a user who has a particular site. It's a renewable energy developer who has a site at a specific location and wants to see whether they can use it with a certain configuration of RE to produce ammonia, and what cost will that give us. In both the cases, there are two kind of inputs, that two parts to the dashboard. The left hand side has the inputs and the right hand side has the outputs. The output dashboards are the ones that I showed you in the slide. They have the ammonia outputs, the hydrogen outputs, and the renewable power outputs. The outputs are for the production, the cost, and the operational profile. And then there are outputs which are for the end products and the breakup of the capex, as well as the breakup of the levelized cost of hydrogen and ammonia and the contribution of that. This will get populated as we will fill up the cases. On the left hand side, we have the input sheets. Every cell that is in the orange background can be changed via user input. All cells which have orange font but are in gray background, they should not be changed, because these are all calculated numbers that are coming from the sheets that are behind, which are these sheets. We will talk about them in the end. So just to take you through the dashboard has two main input parameters, that is the plant design parameters and the financial parameters. The plant design parameters include the definition of the green ammonia that has to be there, that is, what is the definition of hydrogen that is being fed into the green ammonia plant? Is it monthly or hourly? You can select a value from the drop-down list. What is the target ammonia plant capacity that needs to be put in here? You have to select any value above 50 KTPA per annum. What is the year of installation of the plant? This is a 10-year window, and you can drop down and see the 10 years. So we have selected here, let's say 2027. As the year in which we want to set up the plant. What is the RE generation technology that we are using? Here I can choose a combination of onshore wind, offshore wind, solar plus onshore wind, and solar plus offshore wind. Because I am using monthly configuration, it does not show me a lot of battery options, because I'm going to anyways use grid to support my power requirement, and I would probably buy power from grid as compared to putting in battery because of banking benefit. So hence this doesn't show. If I were to show you how it would show in the hourly case, you will probably see the RE generation technologies that battery options have opened up here. But we go back to the case of monthly to do the cost calculations here. So we select here monthly. We select RE generation technology as solar plus onshore wind. We select the RE and hydrogen ammonia plant configuration, and we want it to be grid connected. We will select the geographic location of the plant. We wait for the calculation. The calculations have to finish running. And we select Gujarat as the case for our demo, default values. And RE grid, plant grid connection, whether it is connected to the state grid or the central grid. Let's take it as the state grid where we are connecting the Gujarat plant. What is the location of the hydrogen ammonia plant? Because we are setting up a plant in Gujarat with a grid connection, we can, and selected at the state grid, we select Gujarat as the option. What is the location? What is the grid connection? Whether it is STU, CTU, we select STU. Whether we want to take banking or no banking, we select grid banking as an option. And we choose alkaline as a technology and grid curtailment rate as 1%. And the debt interest ratio has been taken as 0%. We'll take it as, let's say, 7% here. And we'll take debt share to be 40% and the target IRR to be 12%. So here the weighted average cost of capital is around 10%. So at this weighted average 10%, the cost that comes out, this whole Excel sheet gets populated, the entire output starts to come now. So as you can see, we see the ammonia production is at 90% PLF, that out of 100 KTPA our RE plant configuration, that is of solar plus onshore wind with grid connection, will be able to produce at 90 KTPA. The hydrogen plant is running at 90% PLF, it produces 16 KTPA of hydrogen, and the renewable plant is producing at a PLF of 26%. It gives different costs. So the ammonia that is being produced is at $0.6 per kg. The hydrogen that is being produced is at $2.81 per kg. And the electricity that we are producing is at $32 per megawatt hour. The operational profile of the ammonia plant is pretty flat. It goes up and down as the renewable goes up and down a little bit, but mostly it remains flat because of the support of grid banking. And the power is running primarily on the direct connection of the grid plus the RE plant. So there is no battery, as we had also not configured in that. So this is how the dashboard runs. This is also a dashboard that is there in RE. In order to select this dashboard, you have to toggle the sheet by selecting this checkbox, and then this sheet gets activated. And here, as compared to the other dashboard, we do not select the target ammonia capacity, we select the target RE capacity, and where are we selecting that RE, and it will do the necessary calculations for ammonia, hydrogen, and renewable power. And we'll also give the same breakups as we go along. Right. In this dashboard, a user can also, depending upon the configuration that has been given here, can, if the user sees that, okay, I do not want to use the same configuration that has come, the model has calculated, I can manually design a plant. In order to do that, I'll first deselect this one. This is deselected. I'll select this checkbox, and then you will see that some of the calculated values have now been converted into orange background. That means the user can now start inputting it. So now, if I were to provide some oversizing of the electrolyzer, that is, I want to oversize my renewable as well as my electrolyzer plant, I can do that. RE plant oversizing right now it's 260%. Maybe I want to get to 400% oversizing of RE so that I put up a larger renewable plant and a larger electrolyzer, and I want to maintain the ratio solar to wind, and then I see what my cost numbers are. So as you can see now, the PLF has gone up to 99.4%. and the cost has gone up from $0.6 to $0.7 per kg. So there is always a trade-off as to whether I want to run the plant to the full capacity or the cost to be minimized. If the user wants to change the configuration and see what ways in which the plant can run, then the cost can be calculated here. So in order to now demonstrate how the model runs in different cases, what we have going to do is going to run 3 specific cases. We are going to take a 100 KTPA plant. We are going to run a plant on both hourly settlement as well as monthly settlement. We will do one case for hourly settlement and two cases for monthly settlement. The plant will be commissioned in 2027. For the hourly settlement case, we will take the technology as solar plus wind plus battery. We will take the plant to be directly connected to the grid and to be located in the STU of Gujarat. And then we are not going to take any banking as part of that and going to use alkaline technology. Then we're going to run the other two cases. The first case of that would be that we are going to take the monthly settlement for a green ammonia, commission the plant in 2027, use only solar as an electricity source and use grid connection to be able to supply the electricity when the solar plant is not running. We are going to set up the plant in the best location where there is solar, that is CTU in Rajasthan. And we are going to wheel the power to UP and going to connect the ammonia plant into the STU because we want to take the banking facility. We will select banking as yes, and we will keep the electrolyzer technology at alkaline. And the third case we are going to use is the same configuration, but we are not going to take the banking. And because we are not going to take the banking as a benefit, we are not going to connect the plant to the STU, but we will only connect it to the CTU. So we are going to run these three cases over the next 15 minutes and see how the results come. We'll keep the debt to equity ratio in the same across all of these configurations. So I go back to my dashboard. I can maximize this. Okay. So I'm going to use the same dashboard and I'm going to come up with these three cases. So the first case is that I'm going to take the hourly settlement case. So I'm going to go to the dashboard. As soon as I select this, you will see everything will get reset. This has been set by a macro. So I select hourly as a settlement. Then I want to configure my plant as 100 KTP in 2027. My RE generation technology has to be solar plus wind plus battery. So I select solar plus onshore wind plus battery configuration here. Then I want to select the plant configuration, which is going to be my directly connected plant. Then I want to select my renewable energy plant location, which is in Gujarat. I decided that I would want to set it up in STU in Gujarat. This is direct connection. And then for the balancing, I had taken that I will not take any banking as the case. So this gives me a certain output, which is that the ammonia is running at a PL of 90%. The plant will be shut down for 750 hours because there will not be direct electricity that will be available to be fed into the grid. And the cost of ammonia is coming out to be $0.95 per kg. The plant is running either directly on RE because we have not chosen any other grid connection, or it is shut down for these many hours as it goes along. And hence how it is running. Then the second case that we had to run was to compare was on the monthly settlement. So as soon as you select it, it gets reset. Again, the plant configuration remains 100 KTPA to be commissioned in 2027. The RE generation technology here we had chosen was solar only. We wanted to set it up in the CTU of Rajasthan, which is the best location for one of the best locations in India for solar. So we're going to select Rajasthan here. We're going to put the plant on the CTU here to save the state level charges and losses. We're going to set up the plant in Uttar Pradesh. We want to avail the grid banking as a facility, so we'll connect it on the STU. We will put the balancing mechanism as grid banking. We will keep that curtailment rate as 1% and the debt and the financial parameters the same. As you can now see that with grid banking, the plant is running at 100% for its configuration, and the cost has come down from 0.95 to $0.61 per kg. The cost of hydrogen is $2.9 per kg, and the plant for hydrogen is running at 90.9%. Now let's say I want to change this configuration where I am only moving away from the banking case to the no banking case. So what I will do is I will now connect the plant at the CTU of UP, and I will take the case of no banking. So we are waiting for the calculations to get over. So as you can see, the plant is running at 100% capacity. Because we are not taking any banking facility, but we are still running on the grid. And the remaining power, that is when sun is not available, is coming from the exchange. The plant is still running at 100%. The cost has gone up from $0.6 per kg to $0.8 per kg. The cost of hydrogen has gone up from $2.8 to $4 per kg approximately. And the plant is running in direct RE only for a very specific period of time. It is running on RE plus grid for another specific period of time, which is 1100 hours. And then only grid, that is for 4000 hours, we are buying electricity from the exchange and are paying all the charges around that. And this is also the configuration that is seen for the hydrogen plant. So this is how this looks like. And if we go to the numbers here in the PPT, how the plant configurations have changed and the numbers, how they come up differently. These cases have been fed into the model as well. So you can select any state, any site in the country, and it will start feeding the numbers and it will start giving out numbers. Based on all of these calculations, what we have found is that the cost of green ammonia can go down by up to 20%, 16 to 20% under different configurations over this decade. Even though there is going to be extremely high cost reduction in the cost of electrolyzers, there are a lot of other inputs that go into it. Overall net effect is that 20% cost reduction is going to be seen in the cost of green ammonia. There is a very high sensitivity of the cost towards the weighted cost of capital. We have taken a 10% weighted cost of capital in the demo that I showed you. In the calculations that we have given in the report, we have taken the cost as 10.7%. And if we take the cost to be on the lower side, the cost can come down to be approximately 20-25%. So there is a very, very high sensitivity to the cost of weighted capital. And the costs are also very sensitive to the way the ammonia plant is to run. If the plant can be shut down for a large number of hours, that is when the RE is not present and I can sort of shut down my ammonia plant, then my cost of electricity goes down because I do not need to add up any battery or need to buy electricity from the grid. But if my plant has to keep running even when my RE plant is not producing, then I have to put in expensive batteries, I have to buy power from exchange, I have to buy power from the grid, which is all very expensive, and they add a lot of cost to the ammonia. We have tried to give users an input to be able to change the configuration at the cost of ammonia in this. So now to take you through the next part of the model, which is what are the structure of the inputs and the sheets. So this is how the model dashboard looks like, but there are other sheets here. These are all the sheets which are the processing sheets that are running and are calculating. Then the sheets in the gray are the ones which are input sheets. So there is a sheet which has inputs for all the power related assumptions that have been taken. There is a sheet for all the assumptions that have been taken for hydrogen, ammonia, and fertilizers. There is a sheet which has all the site configurations that have been taken into the model, because once you select a state and select the RE plant configuration, then the RE plant configuration is calculated based on the resource available on the various sites. And we have done some optimizations on the basis of these sites and the different RE configurations and technologies that are available as to what would be the optimal solution for the lowest cost of green ammonia that is there, and these are all coded here. And then there is a sheet which just talks about the different drop downs and the ranges that are there. We've also provided a library of all the sources that have been used to calculate and as well as to take these assumptions. This is a very good library, which is very comprehensive and talks about all the aspects that are there as part of that. So I'll take you one by one through this. So in the sites sheet, all the sites are there. So you have all the solar sites across all the states, all the wind sites, as well as all the offshore wind sites. And then when the user selects the technology, it takes the specific state, looks up the value, puts them in this table, and then calculates the production that is there on an hourly basis for each of the configurations. So once the annual site production numbers are taken, they are converted into the units of electricity produced, and then they are allocated towards different parts of the plant, whether they are going towards the production of hydrogen in the electrolyzer, whether they are going and running the ASU, whether they are going and running the ammonia plant, whether they are charging the battery, or whether there's some sort of operations which is coming from the battery and then running the electrolyzers. All of this has been configured here, and this has then the input values that are taken for the hydrogen and ammonia are then used in the cash flow statements, and we have then taken all the other capex and opex elements against this revenue that has been generated to calculate the discounted cash flow. This has been done on the NPV level using the weighted average cost of capital to calculate the cost of LCO, LCOH, and LCOE. This is a bridge sheet which takes all the inputs that a user puts in the input, gives it to the operation sheets, and then which are then used to give to the cash flow statement. So in the sites sheet, you can change your site. You can add a custom site here in this orange column and select a custom site from the model, and it will pick up. In the hydrogen ammonia fertilizer sheets, all these cells which are in orange background, they can be user configured, and they can be default values have been given here in orange font. If somebody wants to revert back, they can always copy paste these numbers here. If they want to put their own numbers, they can be done in these orange cells here. Similarly, for all the power related inputs that are there, they are also given as a user input that can be changed. You can change a number here in all of these orange cells, and that will reflect across the model. If you want to revert back again to the default values that are there in the model, these are in this, and you can just copy the numbers back into this, and this will work. This is a very sensitive column, this column D in power and column D and E in hydrogen ammonia fertilizer assumption, because they take all the inputs that go into the model and how the model is running. The definitions have been given here alongside. So this covers the structure of the model. Thank you so much.